More than a century ago, in a world where limitless energy could be drawn directly from the ether, the invisible sea of energy and structure that fills all space. He wasn't talking about burning coal or splitting atoms. Tesla tapped into something deeper, the primal medium of the universe. But what happened to this vision? Why did the world shift toward wires, meters, and monopolies instead of free, radiant energy? In the early 20th century, a decisive pivot took place. The scientific establishment began favoring Einsteinian relativity over the ether-based field models that Tesla and others worked from. This was no mere academic disagreement. The rejection of the ether paradigm, under pressure from financial and political interests, effectively buried a generation of promising research into free energy technologies. Tesla's Wardenclyffe Tower, which could have transmitted power wirelessly across the globe, was dismantled not because it failed, but because it succeeded in threatening centralized control. Today, a new wave of inventors and thinkers is resurrecting what was once lost. One such breakthrough is the Energy Revolution System, a digital blueprint that empowers individuals to recreate Tesla-inspired energy tech from their own homes. According to a detailed review on Letter Secular Sacred, this system isn't just theory, it's a working plan that leverages high-voltage field dynamics to extract usable electricity from the environment. It bypasses the limitations of conventional generators and taps into the same principles Tesla used in his radiant energy experiments. At its core, the Energy Revolution System works by creating asymmetries in the dielectric field, a concept familiar to those who study ether physics. These field differentials allow the system to generate electrical potential without burning fuel, spinning turbines, or relying on solar panels. Instead of consuming energy, it manipulates it. Users are guided step by step through the process of building their own setup, using accessible materials and straightforward instructions. The result? A decentralized power source that challenges everything we've been taught about energy dependency. As the world grapples with rising utility costs, climate instability, and fragile infrastructure, the rediscovery of ether-based technologies is more relevant than ever. The Energy Revolution System isn't just a DIY project, it's a quiet rebellion against a century of suppression. It's a chance to reconnect with Tesla's legacy, to reclaim energy as a birthright, and to step boldly into a future where power is no longer bought, but built.
This episode is Nikola Tesla's single-wire power transmission Part 2. Previously in Part 1, from November 5th, 2023, the Nikola Tesla single-wire power transmission patent was described, and then my early test setup was introduced. A better-tuned sender and receiver Tesla coil transformer powering a DC fan motor. Here's that Tesla patent for single-wire power transmission. On the left is a sender or transmitter step-up transformer coil. On the right is the receiver step-down transformer coil, and then they're connected by this single wire here. So the high-frequency, high-voltage alternating current from the secondary of the transmitter goes through this single wire to the center of the receiver coil and step down into high-frequency, low-voltage alternating current to power lamps and motors. Transmitted through 4 meters of copper-clad aluminum wire and also through 2 series-connected fluorescent tubes. Now, in Part 2, the setup is evolved. I've got some improved power metrics, and I've made some rectifier benchmark tests, doing it through more transmission media, and also we'll do a brief literature review of some more recent authors. In this episode, I'm transmitting through 12 meters of carbon fiber thread, some water, 3 fluorescent tubes, a couple of other things, spark plug, etc. Look at some plasma effects seen in bulbs, and radiant energy? As before, step-up sender or transmitter coil and my step-down receiver coil each has a bifilar pancake high-voltage winding and a unifilar low-voltage winding around the outside. My Tesla coil driver circuit is the open-source solid-state Tesla oscillator designed by Master Evo. Check out his YouTube channel. So I ordered Master Evo's PCB design, got all the parts for it, and this is before and after. The circuit generates negative voltage impulses to excite the primary coil. The supercapacitor bank, $150 US of high-end Maxwell supercapacitors with a balance board. Technically, it's called an ultracapacitor if you've got an assembly of supercapacitors. We've got the oscillator circuit G generating negative voltage impulses, exciting the primary here. L1 and L2 comprise the step-up center transformer or TX. L1 prime and L2 prime are the step-down receiver transformer or RX. Low voltage windings feed to both sides of this bridge rectifier. a supercapacitor connected in parallel across the plus and minus outputs of the bridge rectifier, running a load of a 12-volt automotive radiator fan motor, acrylic disc instead of fan blades. Typically, I've been running it with this setup where the receiver is grounded as well as the transmitter side, but some recent authors suggest that it can be done without grounding the receiver. So I'll also have a demonstration using a conductive body as opposed to a ground connection at the receiver. Let's see it in action. The oscillator circuit is a high-side MOSFET switch. It excites the primary coil using back EMF inductive spikes. The timing is set by the function generator through those two BNC ports. And we've got the transmitter coil over here. Its output goes out the window, out into the parking lot, to the receiver coil. On the right, you can see what the thread looks like. The line's barely visible, but I've drawn a bracket around it here. So just to try and get a benchmark on this transmitter, I'm gonna just turn the power on and leave it at 2 times 12 volts. So that's 24 volts DC. Secondary voltage is at 960 volts peak to peak. Around at 128 kilocycles. Let's go check the receiver. Over here at the receiver coil, we've got the carbon fiber thread coming into this pylon. It enters into the center of the receiver coil. That's got a voltage probe. You can see 15 volts here at the rectifier. And this black box here is just the pulse width modulator to control the motor speed. So let's turn it up. Oh yeah. How's the voltage doing? 13.4. It's got a pretty good clip. It's hanging tight at a little under 14 volts, 1 amp. 916 volts peak to peak, 128 kilocycles. There you go, 13.7 volts, 1.1 amp. Is our little rudimentary power reading. So yeah, we've got a 12-meter long carbon fiber thread, single wire transmission line, delivering about 15 watts to run this motor. Good ways away with minimal losses on the wire. I mean, it's got over 1,000 ohms resistance. And the end of the line, 916 volts peak to peak, is within 10% of the start of the line. So it's not like Ohm's law is being followed. The transmission line with the resonant center and receiver coils, it's an electric field oscillation. It's not a conventional conduction current, is the hypothesis we're looking into. However, keep in mind that if you take your attention away from the system, it will go on charging the capacitor over voltage, and then you'll have to discharge it, like this situation. Oops, I overcharged it. No harm done, and this experiment having gone fairly well, I thought I'd try transmitting through a carbon fiber thread out to the parking lot and then back into the apartment through some irrigation tubing of water, but unfortunately I got nothing from it. No signal inside. What did work was transmitting through this little tray of about 4 centimeters of water. You can see there's an electrode from the transmitter on the right and to the receiver on the left. This is just plain tap water, and it transmits just fine through tap water despite the low conductivity. And what's interesting here, you'll see me pouring in some baking soda, making it more conductive, and yet the voltage waveform on the oscilloscope stays level. The amplitude doesn't change, so that's a bit unexpected. Let's look at a few more recent sources and see if they can explain what we've noticed. The single wire patent was so pioneering that it came out before diodes even existed. Fast forward to the 1990s, and the first modern diode rectifier for single wire transmission lines comes from this patent from 1993. And here's the US version, granted in 2000, by 2 Russian gentlemen, Stanislav and Konstantin Avraменko, called Method and Apparatus for Single Line Electrical Transmission. So let's just quickly skim through this one. I just wanted to look at the abstract and then figure 4. Associated apparatus for supplying power to an electrical device, including generation and subsequent transmission thereof to a receiving device via a transmission line, the method being characterized by the transformation of the electrical energy which is generated into the energy of oscillation of a field of free electrical charges, such as the displacement current or longitudinal wave of an electrical field, the density of which charges varies in time, and the transmission of the energy via a transmission line which does not form a closed circuit, comprising a single wire transmission line, and where necessary, its transformation into the electromagnetic energy of conduction currents. So they're distinguishing between oscillation currents and conduction currents. This is the crucial drawing. Check out Figure 4. Figure 4 shows the power supply diagram for receiving devices operating on direct current. To supply power to electrical devices operating on direct current, the output of the single wire transmission line 4 is connected to an accommodation circuit in the form of a diode circuit, such that the output of the single wire transmission line 4 is connected to the common point of the anode of the first diode VD1 and the cathode of the second diode VD2, while the cathode of the first diode VD1 and the anode of the second diode VD2 are the outlets 01 and 02 to be connected to the receiving device 5, either directly or with a capacitor connected in parallel. Or alternately, a transformer circuit employing two interconnected inductors L5 and L6, such that the receiving device 5 is connected to the inductor L5 via the rectifying circuit. So that's just saying that there's a sender and a receiver, like we're doing here. Notice that the top version is actually running straight off the high voltage single wire line. There's no step down transformer. And then notice on the bottom version, there is a step down receiver coil, but it's not grounding the high voltage part of the receiver. It's connected to a conductive body. That was the original Avermenko patent. And then a few years after that, Tremkov and Avermenko, single wire electric power system for renewable based electric grid, abstract. He describes it as a reactive capacitive current for transmission of active electrical power. We've got a Tesla transformer applied to the generator site to generate high-frequency reactive capacitive current, and a reversal Tesla transformer and standard rectifier and inverter at the user's end to convert the reactive high-frequency electric power to standard 50 or 60 hertz electricity. A single-wire electric power system has quasi-superconductivity property for reactive capacitive current flow along the line even at high operation temperature of the electric conductor. It has no resistance losses for the following tested conductor materials: copper, aluminum, steel, tungsten, carbon, water, and damp soil. I have so far tested it with copper, aluminum, and carbon and water. I like the way Tremkov describes it. Discussion. The step-up Tesla transformer generates during a half cycle the charges of high density and high electrostatic potential. The free charges are moving along the line from generator site with high potential to the user's end with small potential, and this capacitive charging current is stipulated by Coulomb forces. These charges are moving on the surface of the wire, and the current is not affected by Ohm's law and Joule law. So, Tesla transformer is operating during one half cycle as an electrostatic generator, continuously generating free charges and supporting high potential at the generator site. In the following half cycle, there is a change of the sign of charges, which are recharging the line capacitance. A displacement current in the space surrounding the wire corresponds to change of an electric field strength. The displacement current, as well as capacitive charging current, is not affected by Ohm's and Joule law. 100 years ago, Nikola Tesla developed his apparatus for transmission of electrical energy using single-wire technology. He considered that one terminal of the secondary and primary coil of the step-up and step-down transformers must be connected to the earth. That means that the single-wire line can be applied only to the power transmission along the earth. Now we know that electric power can be transmitted to anybody not connected to the earth. For example, to an air balloon, plane, or even to satellite. We don't even need to apply a step-down transformer for single-wire power transmission. We can use for power transmission non-metallic conducting media like isolated water tubes, cables made from carbon, or conducting oxide on glass. We developed single-wire electric power system using laser beam as a single-wire line. What? New principles of electric power transmission using capacitive and displacement current. In the future, these can be applied for the construction of united global solar electric power system for the world. In conclusion, the single-wire electric power system uses a one-pole, single-wire, open-tuned circuit, capacitive and displacement current for transmission of active power. Modified step-up Tesla transformer was applied to the generator site to generate high-frequency reactive capacitive current, and a reversal step-down Tesla transformer or diode capacitor block was used at the user's end to convert high-frequency reactive power to a standard 50 Hz or DC electricity. So we've got the sender coil on the left in figure B, the receiver coil number 7 on the right, and a rectifier here in the load. So that's more or less the setup I've been testing. And then that led me to this expanded version from textbook, chapter 19, by Dmitry Strepkov and others, single wire resonant electric power systems for renewable based electric grid. And I just want to skim over some of this stuff, just check out what kind of things they're suggesting here. At the beginning of the 19th century, there were no diodes and transistors for pumping resonant circuit and a transformer. Nikola Tesla used the method of impact incitation with a spark arrestor with 96% transmission efficiency. At the end of the 20th century, we used a thyristor frequency converter with 25 kilowatt capacity, water cooling with 86% efficiency and 400 kilogram weight. Currently, frequency converters on silicon transistors with 97% efficiency and 30 kilogram weight are applied. That sounds like progress to me. And even more lately, 20 kilowatt inverters on silicon carbide transistors with 98% efficiency. Covers the same patent drawing as I've been interested in. Goes through a comparison of classic electric engineering based on the use of alternating current in a closed circuit versus Nikola Tesla's electric engineering based on the use of reactive current in an open circuit line. Anyway, trends of future development of electric engineering and the energy industry. So Nikola Tesla has left behind the following technologies for further development. 1. Single-wire resonant technologies for power supply to stationary consumers. 2. Technologies for wireless power supply to service and sea transport. 3. Technologies of directional electric power transmission through conducting channels in atmosphere and space. In the 21st century, these technologies make it possible to develop 1. Fuel-free rockets with electric rocket motors. 2. Extremely long-range electric power transmission lines with lower losses than in superconducting cable lines. 3. A unified energy system. 4. A global solar energy system with terawatt transcontinental power exchange and 24-hour electric power generation. For a million years in the amount of, terawatt hours. Strebkov in this piece is talking about using single-wire transmission lines to interlink all the different continents of Earth, collecting solar power 24 hours a day wherever the light is, and transmitting it all around the Earth. The global solar power system. In order to set up the global energy system developing Nikola Tesla's ideas, we proposed electric energy transmission through high voltage, single conductor cable, gas insulated lines, and the use of 3 solar energy plants in the deserts of Australia, Africa, and Latin America as energy sources. Thus, Russia proposed the model of the future world development based on direct conversion of solar energy at solar power plants and transcontinental terawatt power streams with the use of resonant waveguide technologies suggested by Nikola Tesla. Single conductor cable lines covered by Nikola Tesla's patents will replace overhead electric power transmission lines, which will considerably increase reliability of electric power supply, reduce rates of injuries caused by electricity, and free considerable areas of fields, cities, and forests. Humanity will be able to unify energy systems of all the countries into a global solar energy system of the Earth to provide decent living conditions for everyone and to implement large-scale scientific and technological projects, both on the Earth and in space. Heavy stuff. So I'm going to just conclude with that. Couldn't have said it better myself. Now that we've seen the Evermingo patent and the guide for how to make rectifiers, I'll show you some benchmarks of the rectifiers I've been working with. Basically, I'm making a bridge rectifier out of 4 diodes and different diode types. The front runners are Schottky diodes, ultrafast or ultrafast with soft recovery as well. The way I've been doing benchmarks is by maintaining the supercapacitors around 12 volts while powering the DC load, and then I'll compare the input power, the DC power supply, the transmitter side, to the output power, the rectifier and supercaps measurements at the receiver side. And that's how I compare the efficiencies. A big improvement over last time is I've got now the 4-channel tablet oscilloscope showing the receiver voltage and current waveforms and the diode response. Probing the rectifier, it's a real good picture of output to the circuit. My receiver is typically grounded, but also I've tested with an ungrounded receiver because that could open up a lot more possibilities for receivers if they don't have to be touching the earth. This is to serve as a demonstration of the practice and learning process, discovering which metrics I need to be watching and trying out the hardware, but disclaimer that I'm not an expert of the science. This is just development. The best efficiency I've achieved is still only 39% for my system so far, but then again, part 1 video claimed only 20%. Here's a setup to test the performance of a few different rectifiers I've been working on. We've got the step-up transmitter coil, high voltage output from that, going through the single wire into the step-down receiver coil. Its low voltage output goes into this rectifier, which turns it to DC, charges the supercapacitors, and our DC loads run off of that. The tablet oscilloscope is probing on the receiver the high voltage input, the low voltage output, the current into the rectifier, and the DC output from the rectifier. First up, we've got the full wave bridge rectifier of Schottky diodes. The yellow trace is the high voltage input coming from the sender coil, and then the blue is the low voltage output that's leaving the receiver coil and going into the rectifier. Pink trace is the current from the receiver low voltage winding into the rectifier. And then finally the green is the DC voltage of the rectifier and supercapacitors. Alright, 12 volts, 1.5 amps on the receiver, 24 volts, 1.9 amps on the sender. Swap in for the full wave bridge rectifier of ultra-fast silicone diodes. .1 volts, 1.4 amps on the receiver, 24 volts, 2 amps on the sender. Let's get a look at those waveforms. And finally, here's a test with 4 ultra-fast soft recovery diodes. .12 volts, 1.4 amps on the receiver, 24 volts, 1.9 amps on the sender. Shocky, ultrafast, and ultrafast with soft recovery. A characteristic of note is their fast recovery time. That's talking about reverse recovery, when the diode's going from being in conduction mode to being shut off not conduction mode. That's often where the power losses are occurring if the diode's not switching fast enough. Soft recovery means that shut off during reversal is done non-abruptly, but it turns out these all perform quite similarly to each other. Here's the oscilloscope readout side by side of each different kind of diode. We can see the Schottky diodes outperform the other types, but only by a very small margin. I'd been hoping to see a more dramatic difference, but this is also good to know. Take a look at the yellow trace versus the blue trace. The primary and the secondary of the receiver coil look to be slightly out of phase, but I believe this might be measurement error caused by my using a low-pass filter on the oscilloscope. I found another screenshot that did not have the low-pass filter on, and there was no phase shift, so the apparent phase shift may just be a measurement error. That's something I'll need to look into further. Now let's take a look at running with the receiver connected to ground versus having it ungrounded, connected to just a conductive body. With a grounded receiver, we're getting 12.3 volts, 1.5 amps, and on the transmitter, we're 24 volts, 2 amps. Now, let us unplug the AC mains ground. Here's the foil-covered box I'm using as a conductive body. Drop to 12 volts, 0.4 amps on the receiver, and 24 volts, 0.8 amps on the transmitter. 38% with a grounded receiver versus 25% with an ungrounded receiver. In the Everminko patent, it says it needs a conductive body of sufficient size, so I may just need a larger box. Here's a clip from the classic Eric Dollard and Borderland Science Research Foundation longitudinal electricity video. You can see Eric Dollard is suspending a sheet of aluminum foil from a piece of tape, and the foil is attracted to the bulb when it's lit through the single wire transmission line. They're calling this radiant energy, citing the Nikola Tesla patent for that. And after the Dollard clip is a clip from Adrian Marsh, and he's got a great video about it.
The longitudinal mode, this pressure wavefront, is what Tesla was talking about in terms of radiant energy, radiant matter. But those beams that he drew in his patent are what we are observing now. So rays that extend outwards from the source.
And then I decided to try unplugging the receiver coil and just plugging the single wire straight into this little compact fluorescent bulb next to a sheet of aluminum foil suspended by a tape right beside it. And we can look at some radiant energy effects, y'all. Just the compact fluorescent bulb lit via the single wire transmission line, it attracts the piece of aluminum foil into itself. So with this compact fluorescent bulb, one pole is the single wire transmission line input, and the other pole is what Adrian Marsh calls a fly lead. It's just a long piece of cable connected to nothing. So in effect, this thing's not located at the end of the transmission line, but that it's midline where it's less reflections and such. All right, so here we go. When we light up the bulb, you'll see the aluminum foil sheet drawn into it. So this one is just a 12-volt automotive bulb. When I run the single wire power through it, it doesn't want to light up unless I touch it. And then it likes to go all plasma blue by me. Little plasma arc discharge phenomena. Here we have an automotive 12-volt turn signal indicator bulb. Looks like the top filament might be broken in there even. Cool. That's wild. I had previously powered a load through the two straight fluorescent tubes here, but I've added the third ring bulb at the top and I really like it. The scope screen on the top right shows the transmitter voltage, the blue trace, and the receiver voltage, the pink trace. We can see how the receiver voltage stays flat until the transmitter voltage is high enough to ionize the gas inside the tubes and make the plasma conductive, and that's when the receiver voltage jumps up, is when the lights reach their peak brightness. Notice the very slow response time. I have not yet found a way to get a screen record or screen capture for this scope without having it be painfully slow, so please pardon the lag there. Illuminating it inductively. The line is going around the bulbs, but it's not touching any of the metal contacts. The straight tubes aren't even near the wire, they're just up against the ring bulb. Slightly surprising and interesting was these little shadow stripes that spiral around the bulb, showing where the wire was previously wrapped. And one last transmission through plasma. I'm going to show a particular bulb being connected in series between the sender and the receiver coils, and then also just connected directly to the sender without the receiver, with and without a fly lead. This is a high pressure mercury vapor lamp bulb. And this bulb does in fact put out UV rays and it generates ozone, so sometimes these are used for disinfectant purposes. The bulb has got the single wire line from the transmitter coming into here, and then the bottom, this wire is connecting to the receiver coil, so it's in series between the transmitter and the receiver coil. But see what happens if I take it off the receiver coil, just straight off the high voltage single wire line from the transmitter. It will light up, but not as bright. So it doesn't light much. Let's try again a fly lead. Taking just a short length of cable, connect it to nothing, touch it to the end. Oh yeah. So no fly lead, dim. Fly lead, rather bright, but even brighter is being connected to the receiver coil. Whoa! Well, cool. Look at that. Is it burning the oil from... And that concludes this massive half-hour long episode. We covered a lot of ground, perhaps too much ground, but I want to thank all of you for watching. I look forward to reading your comments. Feel free to hit like and subscribe. As we close it out, here's some shots from my new digital microscope of 12-volt automotive bulbs connected to the high-voltage single-wire transmission line. We can see the bulb arcing to the bottom where the aluminum platform is, and when I press my finger to it, it arcs to that spot as well. Look at the little grains in the bottom of the bulb there, bouncing around and affecting the plasma. I think those are some oxide from off the filaments, but notice the way they glide around and also seem to cast shadows in the plasma. I can't really say much about it, but I think it's fascinating to watch.